In this video, we are going to sketch curves based off of first and second derivatives. So let's discuss some recaps that we have learned first. If a function is increasing, then its derivative is going to be positive. So if a function is going up, then the derivative is going to be positive numbers. If the original function is decreasing, meaning the function is going down, then the first derivative is going to be negative. B, if the first derivative is increasing, so if the first derivative is moving up, then the second derivative is positive. And conversely, if the first derivative is decreasing, then the second derivative is going to be negative. Part C, if the second derivative is positive, that means the original function is concave up. Think smiley face. And if the second derivative is negative, then the original function is concave down. Think frown face. Part D, if the first derivative is going from a positive number to a negative number, that means the original function has a local max. Again, because the original function means it would have increased, then decreased, which means it would have gone up, and then it would have gone down, and that would have caused a local max. That's called the first derivatives test. And then conversely, same thing. If the first derivative is going from negative to positive, meaning the original function was decreasing and then increasing, then the original function had a local minimum. Again, these two are the first derivatives test. And then part F and G is where the second derivatives test come in. If the first derivative is 0, meaning there is going to be some type of critical point, and the second derivative is negative, that means there was a local max there. And the reason is if you think of an original function, if you have a 0, meaning you have a 0 slope, okay, which means the first derivative is 0, and this is negative, meaning it was concave down, which it is. So we have a concave down and we have a 0 slope. This is going to be a maximum. It reaches its max point and then heads down. And then conversely, if the first derivative is 0, meaning a 0 slope, horizontal slope, and the second derivative is positive, meaning it's concave up. So it means you have concave up and you have a horizontal slope. That means this was a local minimum. So if we think of it in terms of actual graphs, if the original function was decreasing and then increasing, that means the first derivative graph was below the x-axis, negative numbers, and then above the x-axis, positive numbers. Where it crosses at 0 is going to be that minimum point, going from a negative slope to a positive slope. Conversely, same thing happens. If it's going positive, increasing, decreasing, increasing, the first derivative had a positive number, and then negative numbers, and then positive numbers. And again, decreasing, increasing, decreasing, increasing. Every time it turns from decreasing to increasing or vice versa is where it's going to cross the x-axis. So some guidelines for actually sketching these graphs. You want to look for the domain. You want to check the intercepts. X-intercepts, where it crosses the x-axis, where it crosses the y-axis. Is it symmetrical? Think of it especially like sine of x and cosine of x. Those are even and odd symmetry. Look for asymptotes, meaning anytime you have an undefined, undefined, which would be the denominator would be 0. The intervals of increasing and decreasing, this is where the first derivative will come into play. Local min and max values, same thing. The first derivative will come into play. Concavity and points of inflection would be your second derivative, and then from there you will sketch the curve. So let's begin an example. We want to sketch the curve of y equals x to the 5th minus 5x. So the first thing I'm going to do is go ahead and figure out what is my first derivative. So I'm going to get 5x to the fourth minus 5, and I'm now going to set that equal to 0. So now if I divide by 5, I will still get 0, and I'm left with x to the fourth minus 1, which will give me x squared minus 1 times x squared plus 1, which would give me x squared minus 1 equals 0, and x squared plus 1 equals 0. So I'll get x equals plus or minus 1, and x equals plus or minus I. Now we do not have to worry about I, because you cannot graph an imaginary number on a Cartesian plane. But we do know that at 1 and negative 1, we know that something is happening. So if I plug in 0 into, back into here, I will get a negative. If I plug in a positive, it'll get positive. If I plug in like a negative 2 or less, the fact that it's up to the fourth power turns positive. So I know that based off of my first derivative, I know that my original graph will increase, decrease, and then increase again. And now we can talk concavity. So if I was to take the second derivative, I will get 20x to the third, and that's it, because the derivative of 5 is 0. So if I set that equal to 0, that means x will equal 0. So if I was to do the number line, and if I plug in a positive number, I will get a positive. And if I plug in a negative number, I will get a negative. So it looks like it becomes concave down at 0, and then at 0, it turns and becomes concave up. Now we can actually find what these actual points are if we were to plug them back into the original function. So 1 minus 5 will give me a negative 4. And if I plug in a negative 1, I'll get a negative 1 plus 5, which will give me a positive 4. And then if I plug in 0, 0 minus 0 is 0. So I know that at negative 1, 4, that is going to be a max, because it goes from increasing to decreasing. And then at 1, negative 4 is going to be a minimum, because again, it went from decreasing to increasing. And then at 0, 0 is where it changes from concave down to concave up. The other things that we can do is also find where it crosses the y-axis, which we actually just found, because 0, 0, and all the places it crosses the x-axis. So to find the x-axis, sometimes you can find that, sometimes you may have to guess. If I was to take my original function and I was to factor out an x, I'll be left with x to the fourth minus 5. So I'll be left with x equals 0. That is one of my x-axis. And the other is x to the fourth minus 5 equals 0. So at this point, what's going to happen is you're going to have x squared minus the square root of 5, and you'll have x squared plus the square root of 5 equals 0. So if I have x squared minus the square root of 5 equals 0, then I'll have x squared equals the square root of 5, and then I'll have a plus or minus fourth root of 5. So the fourth root of 5 is roughly going to be at about 1.5, roughly. So I know that at negative 1.5, it's going to cross the x-axis, and a positive 1.5 is going to cross the x-axis. So what looks like is this graph is going to be concave down. First, it's going to increase to this point, decrease, and at 0, 0, it's going to turn from concave down to becoming concave up. And that is going to be what the graph is roughly going to sketch like. Another example, this function is differentiable and increasing, and the graph has exactly 2 points of inflection. Now, inflection deals with the second derivative. Which of the following could be the graph of the first derivative? So, if you think about the fact that it has 2 points of inflection, meaning that if you set the second derivative equal to 0, it's going to happen in 2 places. Which means, in order to have 2 inflection points, that means the first derivative is going to have 2 relative max min. Again, inflection point means that it went from concave up to concave down would be 1 inflection point, and then from concave down to concave up will be another inflection point, which means that the first derivative had to increase and then decrease for a first derivative, and then also a decrease to an increase. It would have to have 2 of those. So which of these graphs has 2 relative max or min? This one doesn't have any. 0, max min. This has 1, max min. This has 2. Here it goes from increasing to decreasing, and then from decreasing to increasing. So there are 2 max min. And this one has 3. 1, 2, 3 max min. So therefore the answer will be C. Next, the graph of the second derivative is shown. Which of the following could be the original graph? Now, second derivative, if it is above the x-axis, that means it is positive numbers, which means concave up. So it's concave up there, and the original graph is concave up here. The below the x-axis is going to be concave down, because it's negative. So which of the following functions is concave up, then concave down, and then concave up? So this one is, let's see, this one is concave up, smiley face, and then concave down, frown face. We need a concave up, concave down, back to a concave up. B starts out concave down. This is concave down, so it cannot be A, cannot be B. C, concave up, smiley face, concave down, frown face, back to a concave up, happy face. So we think it's C. D, I think, has too many. Concave up, concave down, concave up, but then it goes back concave down and then back concave up. There's too many of those. So therefore your answer will be C. Next, the graph of the derivative is shown. So you are looking for what is the original. So above the x-axis means it is positive numbers, which means the original function is increasing. Below the x-axis will be negative numbers, which means it is decreasing. So where is it decreasing? The original function is decreasing, going down, and then increasing, going up, and then decreasing, going down. And it cannot be A because it's just decreasing. B starts out increasing, so it cannot be B. C, it is decreasing, and then it's increasing, and then it's decreasing. So I believe it's C, but let's go ahead and check D. It is decreasing, it is increasing, but then it's increasing again, so it cannot be D. Last example, we want to sketch the graph based off of what we know here. Okay, so first thing we're going to do is we're going to draw a graph. Okay, when x is 0, it is, okay, so these are all going to be min and max here because it says derivative. So the derivative 0 and the derivative at 2 and the derivative at 4 are all 0, which means it is either going to be a maximum or minimum. Now, based off of this, I have 0, I have 2, and I have 4. So the first derivative is positive when it's less than 0, so that means it's positive here. And between 2 and 4, it's positive because it's greater than 0, so it's positive. It is negative between 0 and 2, so negative between 0 and 2. And then when x is greater than 4, it's also negative. Then we come to the second derivative. The second derivative is happening between 1 and 3. So it is positive between 1 and 3, and then it's negative on the other side. So it's concave down, concave up, and then concave down. And we also know that 0, 2, and 4, so here's 0, here's 2, here's 4, here's 1, here's 3. So we know that at 0, at 2, and at 4 is 0. We also know that at 0, this is a max because it went from increasing to decreasing. It's a minimum at 2 because it went from decreasing to increasing, and then there's another max at 4. So I'm going to go ahead and sketch this part. So we don't know where it's happening on the graph. We just know that at these x values. So we know it's increasing up to 0. It's decreasing to 2. It's increasing to 4. And then it's decreasing after 4. Now we also know that at 1, it is concave down. And then at 3, from 1 to 3, it's concave up. And then after 3, it becomes concave down. So our final graph, let's make it blue. So the final graph looks like it's going to be concave down and a max at 0. And then from 1 to 3, it is going to be concave up, and it's a minimum at 2. And at 3, it turns concave down again, and some type of max at 4. We don't know if these maxes are at the same height. It could have gone up higher and then gone back down. We don't know that necessarily. We just know that these are relative maxes. And that would be some type of sketch. Your sketch will look different because it can happen anywhere on a graph. We just know that these things should apply.